Okay, so in the last video we talked about how to value test a function. In particular, test where the function has a value of 0 or doesn't exist. Then use those values to look elsewhere. If you know where the function value is 0 or doesn't exist, everywhere else the function value must be positive or negative. And then you can find an idea of where the function is positive or negative. So here, in this case, this question is not asking you to value test the function. This is asking you to complete a first derivative test. So here, note, we're going to be running a value test here on the first derivative. So when we say complete a first derivative test, in a sense, this is just asking us to value test the first derivative. No sweat. So in order to value test the first derivative, we have to know what the first derivative is, but of course we can do that because we can take the derivative of this function. So first step, let's take the derivative of our function just so that we have a grip on the function of interest, and this will be what? 3x squared minus 18x plus 24. Okay, here is our first derivative. Now this is what we want to value test since we were asked to complete a first derivative test. And to value test any function, like this first derivative, we want to test where this function value is 0, where the function value doesn't exist. Now you can actually see very clearly here we've got no denominator, so the does not exist case is not going to come into play, and we simply then have to find out where the function has a value of 0. And to do that, well, just set that first derivative function equal to 0. This is completing what? The first derivative test, right? Okay, so 3x squared minus 18x plus 24. And this is a good old-fashioned degree 2. We can factor this, factor out the 3. You get x squared minus 6x plus 8. And actually that can be factored further because two numbers which multiply to be 8 but add to be minus 6. That's x minus 4, x minus 2. And well, as is the case anytime you have things multiplying to be 0, you know one of the factors must be 0. So in order for this statement to be true, 3 times something to be 0, certainly 3 is not 0. The x minus 4 or the x minus 2 must be 0, but x minus 4 would be 0 when x is 4, and x minus 2 would be 0 when x is 2. So what have we deduced? Well, we know that the function never has a denominator, so don't have to worry about when the function doesn't exist, but we know the function has a value of 0 at x equals 4 and x equals 2. That is good information to have because now we can know that the function crosses the x-axis at 2 and 4. Well, maybe it doesn't even cross. Maybe it just touches the x-axis at 2 and 4, but at least the function encounters the x-axis at 2 and 4, which means these are the only values where the function could possibly have a 0 value, and then everywhere else the function's values will be non-zero, hence either positive or negative. So then we want to find out whether the function values are positive or negative. So, well, let's run the numbers on that. So we need to find a value to the left of 2 to look at to determine if the function is above the axis or below the axis, the first derivative function in this case. So let's take a value to the left of 0, to the left of 2. Let's take the value 1, it's nearby, I suppose. So we could look at 3 times 1 squared minus 18 times 1 plus 24. Note, we were testing our first derivative, right? This is the first derivative test. So ultimately, we are now testing the first derivative value at 1. We know the first derivative value is 0 at 2 and 4. Let's see what the first derivative value is at 1. This is going to be, let's see, 3 minus 18 plus 24. And now, we don't need to know whether or not this value, what this value is specifically. We just need to know whether it's positive or negative. And when you look at that, 3 minus 18 plus 24, you can see that that is definitely positive because, heck, you're 27 into the positives, 18 into the negatives. You know here that your first derivative is positive. But actually, when you think about that for a second, wait a second, first derivative positive. First derivative positive means slope is positive in this region. This means that whenever you look with respect to your original function of interest, since we've done some testing on the first derivative and have determined that to the left of 2 the first derivative is positive, that tells you that your function is uphill in that region. your original function f of x is uphill in that region because the first derivative function has a positive value. The first derivative gives you a concept of slope, and if the slope is positive, the function's uphill. Pretty cool, right? Okay, now next. We need to test between 2 and 4, because we know the first derivative has a value of 0 at 2 and at 4. Let's test between 2 and 4. The natural choice would be 3, I suppose. So this would be 3 times 3 squared minus 18 times 3 plus 24. And now, we don't need to know what this value is specifically. We just need to have a notion of what this value is. So let's run the numbers here. Let's see, that's going to be 27 minus 54 plus 24. When you put all this together, let's see, 27 and 24 makes 51. 51 minus 54. Okay, now we can see this is negative. And we don't, like in particular, I guess we can see that it's negative 3, but we're not concerned about the specific value that it is. We're just worried about the positivity and the negativity. We're just worried about, is the first derivative function above the axis or below the axis? Is the original function sloped positively or negatively? And since our first derivative tests to have a negative value, that means our slopes have a negative value and our function is going downhill. Our function is decreasing in the region between 2 and 4. What about the region to the right of 4? Is the function value, or are the first derivative values positive? Are the first derivative values negative? Is our original function value, is our original function going uphill or downhill? Let's find out. So we need to test a value to the right of 4. How about 5? So this is going to be 3 times 5 squared minus 18 times 5 plus 24. And I tell you what, as I'm starting to look at these numbers and I'm starting to run them, I'm feeling like, man, this is becoming a cumbersome computation, because it's going to be 3 times 25 minus 18 times 5 plus 24. That sounds like a lot of work to compute. And as I think about that, I'm like, man, you know what? We had our original function expressed, our first derivative function, our original expression of our first derivative, as 3x squared minus 18x plus 24. But as we started working this expression, we found out that this expression boiled down to a product of 3 times x minus 4 times x minus 2. And as I think about that, I'm like, you know what? Rather than going through this cumbersome computation here, why don't I just use the factored form? Because hell, that's going to be easier to compute with. So here, 3 times, what is our x? Our x is 5. We're plugging in 5. We're plugging in a value to the right of 4 to find out what the value of the first derivative is. Here, 5 minus 4 times 5 minus 2. And you can see, what? This is all just being multiplied. This is 3 times 1 times 3. And again, well, you can see that this is 9. We don't care specifically what the value is. All we care about is whether this thing is positive or negative. And you can see clearly the value here is positive. And the value here is the value of the first derivative, because we plugged our 5 into our first derivative. And so if our first derivative is positive, that means that our original function has a slope that's uphill. And I tell you what, when you look at this picture and you start to see what's going on here, you can see information about your original function. Because you can say from the first derivative that your original function was increasing between minus infinity and 2 and from 4 to infinity, because the function was uphill in those regions. Since the function was uphill, the function was increasing. You could say the function was decreasing between 2 and 4. That's interesting information. In fact, you could even say more, right? Because if you look at this and you think, like at the point 2, the function went from increasing to decreasing. You know that you have a local maximum at x equals 2. And hey, we haven't gone back to the original function to see what the y value is correspondingly, but we at least know that we have a local maximum at the point 2. Whatever the function value is, we could find out. We could plug back into the original function to see how high the original function is. But no matter, we know we've got a local max at x equals 2. And moreover, look at x equals 4. We know we've got a local minimum at x equals 4. Since the function goes from downhill to uphill, the function must have bottomed out at that point. So the long story short is, while value testing a function is in general just an interesting way to see when a function is positive or negative. When you value test a derivative, you get information about slopes, which gives you information about when the function was going up, when the function was going down, where the function might have gone from up to down, and where the function might have gone down from up, where you've got local maxes and local mins, which is kind of interesting. And that's, in some sense, valuable information to get about the function just by running through a test like this.